All right, welcome back everyone for another deep dive. This time we're taking a look at algorithmics, the spirit of computing. Sounds a little intimidating, right? But trust me, it's fascinating stuff. And don't worry, I've got an expert here to help us break it all down.
Absolutely. We're going to make sure even the most complex stuff makes sense. No need for a computer science degree here.
Exactly. So before we dive into the book itself, I think it's important to highlight that this isn't just for like hardcore coders, right? This is about how we think, how we solve problems, something we all do every single day.
Couldn't agree more. Algorithmics really gets to the core of problem solving. It's about the logic, the steps, the process of finding a solution, whether you're writing code or just figuring out the best way to get to work in the morning.
Love that. So with that in mind, let's jump into Chapter 1, Algorithms and Data. Seems pretty basic, but the author, David Harel, starts us off with a really yummy example, making chocolate mousse.
The perfect way to start, right? And a recipe is a fantastic example of an everyday algorithm. You've got your inputs, the ingredients, the steps you follow, all that mixing, cooking, chilling, and then the output, that delicious mousse.
Okay, so that makes total sense. But one thing that really struck me was Harel's point about the hardware that's actually carrying out the algorithm. Like, if I'm explaining a recipe to a friend, I probably don't need to tell them how to whisk. But a computer, it needs every single little detail spelled out.
That's such a key point, and it's where the concept of abstraction comes in. We need to break down those complex tasks into smaller, more manageable chunks, depending on who or what is executing those instructions.
So it's like tailoring the instructions to your audience.
Precisely. And think about something like calculating salaries for a company. The core algorithm, the steps involved, would remain the same, whether it's a small startup with 5 employees or a huge corporation with thousands.
That's like that one recipe that works for a single serving or a whole party, right?
Yeah.
You just adjust the quantities.
Exactly. It's all about generalization algorithms that can handle a variety of inputs and still get the job done.
So we've got the basics of what an algorithm is, but then Chapter 2 takes us into algorithmic problems and the control of flow. Things get a bit more complex here, right?
Definitely. Because in the real world, things don't always go as planned. An algorithm needs to be robust. It needs to handle those unexpected situations gracefully.
Like, what if that salary calculator encounters a negative salary? It shouldn't just crash and burn.
Exactly. It needs to be able to adapt. Think about it like this. If your GPS suddenly decided you could drive through walls, that wouldn't be very helpful, would it?
Definitely not. I'd end up in a whole lot of trouble. So how do we make sure those instructions are super clear? Harel uses the example of sorting a list to illustrate this.
And he introduces us to a sorting method called bubble sort, which is actually pretty easy to visualize. Imagine the larger numbers literally bubbling up to the top of the list as we compare and swap elements.
Oh, I can actually picture that in my head. It's like those lava lamps, you know.
Exactly. And while there are more complex sorting methods out there, bubble sort's a great starting point. The key is understanding that the flow of the algorithm, the order of those steps, is absolutely crucial.
Speaking of flow, Harel also brings up flowcharts in this chapter. They're basically visual maps of the algorithm's steps, right?
Exactly. It's like a choose-your-own-adventure for computers. They help us see the logic of the algorithm at a glance.
I love that analogy. Makes it way less intimidating. And then within a larger algorithm, we can also have these things called subroutines, right? It's like mini algorithms within the main one.
Exactly. Think of it like breaking down a big task into smaller, more manageable chunks. Like if you're searching for a specific word in a document, that's actually a subroutine happening within the word processor's overall code.
So it's like having specialized tools within your toolbox. Each one has a specific purpose, but together they can build something amazing. But even with the best tools, you're kind of lost without the right materials, right? And that brings us to Chapter 3, Data Structures.
You can't make delicious mousse without good quality chocolate. Data is the stuff our algorithms work with. And just like organizing ingredients in your kitchen, different data structures help us organize information efficiently.
Right, it's all about having a system. And Harel gives us some great examples. Lists, arrays, trees, all these different ways to structure data.
A shopping list is a simple list, a multiplication table is a classic array, and even something like your family tree, with all its branches and connections, is like a tree data structure.
I've always loved those visual representations of family trees, actually.
They're very intuitive. And one particularly cool type of tree is a binary tree, where each node can have at most 2 offspring. Super useful for sorting and searching through massive amounts of data quickly.
Makes sense if you can keep dividing your search space in half, you'll find what you need much faster. But organizing data is only half the battle, right? Chapter 4 is all about getting it together, designing algorithms.
Now we're getting to the heart of it. It's not just about finding a solution, it's about finding the most elegant and efficient one. Harel uses the example of finding the longest distance between any 2 points in a polygon.
Okay, that sounds pretty straightforward.
But if you tried a brute force approach where you checked every single pair of points, it would take forever, especially as the polygon gets more and more complex. A smarter algorithm would only need to compare certain key points, saving a ton of time and computing power.
It's like finding the fastest route through a city you wouldn't want to drive down every single street.
Exactly. And this leads us to a really cool concept: minimal spanning trees. Imagine connecting all the cities in a country with the shortest possible network of roads. Seems simple, but finding the optimal solution has ties to tons of other complex problems.
Wow, so algorithm design is all about being clever, not just brute forcing your way through. But how do we know if our fancy algorithm actually works? How do we prove it? That's what Chapter 5, The Correctness of Algorithms, dives into.
We can test it, of course, but bugs, those little errors, can hide in unexpected places. Harel argues that we need to actually prove an algorithm's correctness, almost like a mathematical proof, but applied to code.
So it's not just a matter of it seems to work. It's about knowing for sure that it'll always produce the right output, no matter what.
Precisely. And there are different levels of correctness, too. An algorithm might be partially correct, meaning it gives the right answer sometimes but fails in specific cases. Like, imagine a mousse recipe that only works if you use a certain size bowl.
That's partially correct, okay. But the real nightmare scenario, the thing we all dread, is the dreaded infinite loop. A program gets stuck, running forever, going nowhere.
Like a GPS that keeps telling you to drive in circles. To avoid that, we use invariants. These are logical conditions that must hold true at certain points in the algorithm. If we can prove those invariants hold, we know our algorithm is on the right track.
Okay, I'm starting to see just how much thought and precision goes into building even seemingly simple programs. It's not just about writing code, it's about logic, proof, make sure it all works as intended. And I guess the next step is making sure these programs don't take a million years to run.
You got it. And that's where we'll pick up next time with Chapter 6. All right, so picking up where we left off, Chapter 6 tackles a crucial aspect: the efficiency of algorithms. Because even the most brilliant algorithm is kind of useless if it takes longer than the universe exists to actually run, right?
It's like having that recipe for the most amazing dish ever, but it takes like 300 years to cook. And no thanks. But seriously, how do you even measure the speed of an algorithm? It's not like we're timing a race or anything.
Right, it's not about clock time, it's about how the runtime scales as the input grows larger. And for that, Harel introduces this thing called Big O notation, which sounds scary, but it's really not as bad as it seems.
Okay, I'm ready. Hit me with it.
Let me put it this way. Imagine walking across a room versus driving across the whole country. The bigger the distance, the more time it takes. That's obvious. But the relationship between distance and time is different in those two scenarios.
Yeah, when I walk, the time increases proportionally to the distance. Double the distance, double the time. But driving, that's way more complex with traffic, road conditions, all those factors.
Exactly. And that's what Big O notation captures, that relationship between input size and runtime. An algorithm that's ON means the runtime increases linearly, just like your walking example.
So ON is like a nice predictable stroll through the park. But what about those more complex algorithms, the ones that feel like a cross-country road trip?
Well, let's take the example of searching for a word in the dictionary. You could flip through every page one by one until you find it. It's called a linear search, and it's ON. But there's a much smarter way.
Of course. If I'm looking for zebra, I'm not going to start at aardvark. I'm going to jump to the Z section and then narrow it down from there.
Exactly, and that's the power of a well-designed algorithm. What you're instinctively doing is a binary search, where you keep dividing the dictionary in half, eliminating tons of words with each step.
Which makes a lot more sense, especially for those super thick dictionaries.
Absolutely, and that's why binary search is so much faster for large data sets. Its big O is actually logarithmic, meaning the runtime increases much slower as the input size grows.
So choosing the right algorithm is like choosing between a leisurely walk and a supersonic jet. But what if even a jet isn't fast enough? Are there problems that are just like inherently impossible to solve efficiently?
You've hit on a fascinating concept, and that's exactly what Chapter 7 explores: the inherent limitations of algorithmics. Because the truth is, yes, there are problems that computers can't solve efficiently, no matter how powerful they get.
Hold on, are you telling me there are things computers just can't do?
Yeah.
I thought they were supposed to be these magical problem-solving machines.
Well, it's not that they can't do them, it's that they can't do them in a reasonable amount of time. Harel uses the famous traveling salesman problem to illustrate this. It's about finding the shortest route to visit a bunch of cities and return home.
Okay, that sounds simple enough.
Until you have, like, 100 cities or even more. The number of possible routes explodes exponentially. Even the fastest computer imaginable could take billions of years to check every single one.
Whoa, my brain just melted a little. So even with all our technological advances, there are still some things we just have to accept will take forever to solve perfectly.
It's humbling, isn't it? And this brings us to the concept of NP-completeness, a whole category of really hard problems.
So these are the problems that keep computer scientists up at night.
You could say that, and it gets even more mind-blowing. Chapter 8 dives into undecidability, the ultimate limitation. Ready to have your mind blown?
Gulp. Okay, bring it on. Undecidable. Like even math just throws up its hands and says, nope, can't do it.
Pretty much. These are problems where no algorithm, no matter how clever, can guarantee a correct answer for every single possible input.
Wait, seriously? I need an example of that. How is that even possible?
The most famous one is the halting problem. Imagine trying to write a program that looks at any other program and tells you if it will eventually stop running or if it'll get stuck in an infinite loop.
To figure that out, wouldn't you need to actually run the program? But what if it does loop forever? You'd be stuck waiting forever.
Exactly. It's a catch-22. And the incredible thing is that we can actually prove that no such program, no solution to the halting problem can possibly exist.
So there are some mysteries that even computers can't solve. That's kind of comforting in a weird way. But speaking of computers, what are they really at their core? Like, how do they even work?
That's the question that Chapter 9 tackles head-on. It takes us deep into the theoretical realm with the universal Turing machine. And it's fascinating because it's a relatively simple model of computation, but it captures the essence of what any computer, from your phone to a supercomputer, can do.
Wait, so you're telling me my phone and a giant supercomputer are basically just different versions of this Turing machine?
At a fundamental level, yes. A Turing machine operates on a tape with symbols, reading and writing to it based on a set of simple rules. You can think of it like a very basic programming language.
It's amazing to think that something so simple can be so powerful.
Right. And the truly mind-blowing part is the Church-Turing thesis, which states that anything solvable by any computer, no matter how advanced, can also be solved by a Turing machine.
Whoa, that's deep. So even if we invent some crazy new technology in the future, the fundamental limits of computation stay the same. That's kind of mind-boggling.
It really is. But what if, instead of trying to invent entirely new computers, we just use a bunch of the ones we have all working together? Could that break through those limitations?
You're talking about parallel computing. Like having a whole team of chefs working on that 300-year recipe, each handling a different part.
Exactly. That's what Chapter 10 explores. Parallelism, concurrency, and alternative models. It's like having multiple cooks in the kitchen, each specializing in a different task. Some problems can be sped up significantly this way.
So parallel computing is like the ultimate time saver then?
For certain problems, yes, but not all problems are created equal. Some tasks are inherently sequential. You can't bake a cake faster just by adding more ovens, right?
That makes sense. You can't rush perfection. But even with infinite ovens, processors, those fundamental limits we talked about earlier still apply, right?
You got it. Parallelism isn't a magic bullet. It's more like a strategy to use wisely. But what about getting a little random with our algorithms?
Random? You mean like throwing ingredients together haphazardly and hoping for the best?
Not quite that chaotic, but Chapter 11 dives into the world of probabilistic algorithms, and it's fascinating. These algorithms use randomness in a very controlled way. It's like flipping a coin to make a decision at certain points.
Okay, but how can a random choice lead to a correct solution? It sounds a bit counterintuitive.
Let me give you an example. Testing if a huge number is prime. Deterministic methods, the ones we've talked about so far, can be really slow for massive numbers. But a probabilistic algorithm can give you a highly reliable answer incredibly fast.
So it's like trading a tiny bit of accuracy for a huge boost in speed.
Exactly. And the probability of being wrong can be made incredibly small, almost negligible. It's a trade-off speed and practicality for a very slight risk of error.
Makes sense. Sometimes you need to take a calculated risk, But what about when we need to keep things secret? Like, how do algorithms help us protect sensitive information?
That's where the exciting world of cryptology comes in, and that's the focus of Chapter 12. Algorithms are truly the backbone of information security, from the simple codes we used as kids to the super complex encryption that protects our online banking transactions.
I've always been fascinated by cryptography. It's like a constant battle between code makers and code breakers.
It really is, and one of the most mind-bending concepts is public key cryptography. It works like this. You publish a key that anyone can use to encrypt a message to you, but only you have the private key to decrypt it.
It's like having a public mailbox that anyone can drop a letter into, but only I have the key to open it. That's so clever.
It is. And the security of this whole system relies on problems that are computationally very hard to solve, like factoring huge numbers. If someone figured out a fast way to do that, it would break the whole system.
So it's an ongoing arms race between creating stronger encryption and finding ways to break it. But let's zoom out a bit. How do we go from these cool algorithms to the actual software we use every day? Like, how does it all come together?
That's where software engineering comes in, the focus of Chapter 13. It's about taking those algorithmic concepts and applying them to building complex systems that are reliable, maintainable, and adaptable.
So it's like the difference between knowing how to bake a cake and actually running a bakery.
A perfect analogy. Software engineering involves choosing the right development models, like the waterfall model, which is more sequential, versus the spiral model, which is more iterative and flexible.
So waterfall is like following a recipe step by step, while spiral is more about experimenting and adjusting as you go, like adding a pinch of this or that as needed.
Precisely. And just like you wouldn't build a house from one giant brick, modularity is key in software engineering. Breaking down the system into smaller, self-contained units makes it so much easier to understand, test, and change when you need to.
Right, because if one little part breaks, you don't want the whole house to collapse. But testing software is a whole other challenge, isn't it?
It is. And it's not just about finding every single bug, it's about managing risk and building confidence in the system. We have unit testing for those individual modules, integration testing to make sure they work together, and validation to ensure the software actually solves the problem it's supposed to solve.
It's like quality control at every stage of the baking process, from checking the ingredients to making sure the final cake not only tastes delicious, but also looks stunning. But speaking of complexity, Chapter 14 takes us to the next level with the challenge of system design. Now we're talking about things like air traffic control, telecommunications networks, systems where failure is simply not an option.
The stakes are incredibly high. So how do you even begin to design something that complex and critical?
Yeah, that's what I'm wondering. Where do you even start?
One approach is to use formal methods, which apply mathematical rigor to the design and verification process. It's like having a team of engineers meticulously inspecting every inch of a bridge, making sure there are no weak points, no potential for failure.
Because even a tiny crack can bring the whole thing down. But how do you even visualize how all the parts of such a complex system interact? It's like trying to imagine all the traffic patterns in a city at once.
That's where visual formalisms come in, like state charts. They allow us to model the system's behavior in a way that's easier to understand and analyze.
So it's like having a map of the city that not only shows the streets, but also how the traffic flows, where the bottlenecks are, and how everything changes during rush hour.
You got it. By understanding those interactions, we can design systems that are more robust and resilient, able to handle unexpected events without crashing.
Okay, after all that talk about complex systems, I think my brain needs a break. Maybe it's time to ponder something a bit more philosophical. Like, can computers actually think? Can they be truly intelligent?
Ah, the age-old question. And it's what Chapter 15, Algorithmics and Intelligence, tackles head-on. But before we can even attempt to answer that, we need to define what think even means. We can build machines that exhibit intelligent behavior, like playing chess at a grandmaster level.
Right, but is that the same as truly understanding the game? Or experiencing the world the way a human does?
That's the debate. And one of the biggest challenges in artificial intelligence is knowledge representation. How do we encode human knowledge and reasoning in a way that computers can actually use? It's like trying to teach a computer about emotions, intuition, creativity, things that are hard even for us to define.
Yeah, it's way more than just logic and rules. So what are some of the different approaches to building AI then?
Well, Harel talks about expert systems, which rely on predefined rules and logic to mimic human expertise. Then there's machine learning, where algorithms learn from data and improve their performance over time.
So instead of being programmed with specific rules for chess, a machine learning algorithm could learn to play by analyzing thousands of games.
Exactly. It's learning by example, just like we do. And then there's deep learning, which uses complex neural networks that are inspired by the human brain. It's already achieving amazing things, but we're still just scratching the surface of what might be possible.
It's both exciting and a little bit intimidating to think about where AI might go in the future.
Definitely. But one thing Harel reminds us is that AI is ultimately a tool. It's up to us to use it wisely and responsibly. And that brings us to the final chapter, the epilogue, where Harel reflects on the incredible journey we've taken through the world of algorithmics.
So it's like we've reached the summit of this mountain of knowledge, and now we're taking a moment to appreciate the view.
Exactly. And what's striking is that algorithmics isn't just about computers, it's about the essence of problem solving, a way of thinking that can be applied to any domain, from baking a cake to designing a complex system.
From the everyday to the extraordinary, it's all about breaking down problems, understanding the flow of information, and finding those elegant, efficient solutions.
And while there are limitations, some problems might be too complex or even undecidable. As we discussed, the field of algorithmics is constantly evolving, pushing the boundaries of what's possible.
So it's not about having all the answers. It's about the journey of discovery, the constant learning and exploration, which is a perfect segue to wrap up our deep dive. Wow, I'm still processing all of that. It's amazing to think about how algorithms are woven into pretty much every aspect of our lives.
It really is. Harold does a fantastic job of showing us that they're not just these abstract concepts for computer scientists to ponder. Algorithms are the invisible force behind so much of what we do and experience every day.
Right. Like, I never really thought of my GPS as an algorithm before, but it's constantly crunching numbers, making calculations to guide me through traffic. And it's not just GPS, it's the search engines we use, the recommendations we get online. It's everywhere.
Absolutely. And it's only becoming more pervasive. Algorithms are helping scientists make breakthroughs in medicine, climate change, you name it. But even with all this power, there are those limitations we talked about, right? Some problems might just be too complex to solve perfectly, even with the most advanced algorithms.
Yeah, those MP-complete problems really put things into perspective. It's humbling to realize that there are some mysteries even the most powerful computers might never fully crack. So it makes me wonder what's next for algorithmics. Are we going to hit a wall, or are there entirely new ways of computing waiting to be discovered?
That's the million-dollar question. It's hard to predict the future, but there are definitely some exciting areas to keep an eye on. One that's getting a lot of attention is quantum computing. It has the potential to completely revolutionize how we solve certain types of problems.
Quantum computing? That sounds like something straight out of science fiction. What's so special about it?
Well, it leverages the mind-bending principles of quantum mechanics to do calculations in a completely different way than classical computers. It's like tapping into a whole new level of computational power.
So could quantum computers be the key to cracking those MP-complete problems that have stumped us for so long?
They might be. But it's important to remember that quantum computing is still in its early stages. There are a lot of technical hurdles to overcome before it becomes practical for everyday use.
I guess patience is a virtue, even in the world of algorithms. But while we wait for quantum computers to arrive, there's still so much happening with our current technology.
Absolutely. Machine learning and AI are advancing at an incredible pace, opening up amazing new possibilities in fields like robotics, personalized medicine, and even art and music.
It's exciting, for sure, but also a little bit daunting to think about the potential impact of AI on society. Will it create new jobs, or will it automate millions of existing ones? Will it enhance our creativity, or make human artists obsolete?
These are questions we need to grapple with as these technologies become more powerful. It's crucial to have those open and honest conversations about the ethical implications of AI. We need to make sure that these tools are used responsibly and for the benefit of humanity.
It's like we're holding this incredibly powerful tool, and we need to be careful not to misuse it. But stepping back from the big picture for a moment, what do you think is the most valuable takeaway from Harel's book on a personal level?
For me, it's the emphasis on algorithmic thinking as a fundamental skill, regardless of your profession. It's about breaking down problems into smaller steps, identifying patterns, and designing solutions in a clear and efficient way.
It's like a mental toolbox that you can use in any area of your life, whether you're organizing your closet or making a major life decision. those principles apply.
Exactly. And I think Harel does a brilliant job of demystifying algorithmics, showing that it's not just this arcane field for computer scientists, it's a way of thinking that anyone can learn and benefit from.
Well, I'll admit, I started this deep dive feeling a little intimidated, but you've really helped me see the beauty and the power of algorithmics. It's changed how I think about problem solving, that's for sure.
That's wonderful to hear. It's been a pleasure sharing this journey with you and our listeners.
We've covered so much ground. From the basics of algorithms to the mind-bending concepts of NP completeness and undecidability. From the power of computation to its inherent limitations. And then, of course, peeking into the future with quantum computing and AI, it's been quite a ride.
It really has. And if you, our dear listeners, are feeling inspired to learn more, we highly recommend checking out Algorithmics, The Spirit of Computing. It's a challenging but incredibly rewarding read that will truly change the way you think about the world.
And remember, the world of algorithms is all around us. So keep exploring, keep asking those questions, and keep pushing the boundaries of your own computational thinking. That's all for this deep dive. Thanks for joining us, and we'll see you next time for another fascinating exploration.